last lecture of this junction breakdown, we have seen the two breakdown mechanisms, that is thermal instability and tunneling effect. Now in this lecture we will see the avalanche multiplication. The avalanche multiplication process occurs when electrons or the holes moving across the space charge region. These moving electrons and holes acquire sufficient energy from the electric field to create electron-hole pairs by colliding with atomic electrons within the depletion region. The avalanche process is as shown in this figure 1. When this electron will come into the space charge region, it will collide with the neutral atom within the space charge and creates again an electron and hole pair, and this original electron which collides with this neutral atom will go in forward direction. Again the electron which becomes free from this neutral atom will again collide with the neutral atom and it again produces an electron hole pair. In this way this multiplication process proceeds. The newly created electrons and holes move in opposite direction due to electric field, because in this p-n junction, on this p side there is built-in potential, that is negative potential on this side and positive potential is produced on this side, and due to which there is production of electric field from positive to negative direction. So this is the direction of electric field, and due to this electric field the electron will move towards the n region and holes will move towards the p region. That is, these newly created electrons and holes will move in opposite direction, and thereby it creates the reverse biased current. In addition to newly generated electrons and holes, they may acquire sufficient energy to ionize other atoms and leading the avalanche process. For most of p-n junctions, the predominant breakdown mechanism will be the avalanche effect. If we assume that a reverse bias electron current iron naught will be reverse biased electron current enters the depletion region at x is equal to 0. This is x is equal to 0. So, and this is x is equal to w. Similarly, in figure 2, this is x is equal to 0 and this is x is equal to w. So, the reverse biased electron current iron naught when enters this space charge region, the electron current ion will increase with distance through the depletion region due to avalanche process. As we have seen in this figure 1, in the avalanche process, due to this first electron, there is production of another second electron. Due to this collision of second electron with the neutral atom within the space charge region, here is again production of one electron and one hole pair. So in this way when this reverse biased electron current when enters to the space charge region, the ion, that is current due to electron, will increase as distance increases. So at x is equal to W, the electron current may be written as ion of W which is equal to Mn ion naught. Mn ion naught. So this is equation number 1, where Mn is multiplication factor. Multiplication factor. The whole current is increasing through the depletion region from N to P region. As this is N region and this is P region, and holes are diffusing from this N region to P region. Here the whole current will increase from x is equal to W to x is equal to 0. So it reaches to maximum value at x is equal to 0. The total current is constant through the PN junction in steady state. We can write an expression for incremental electron current at some point x, which is given by d of ion, the function of x, which is equal to ion of x into alpha n dx plus ip of x into alpha p dx. This is equation number 2, in which alpha n is electron ionization rate. Electron ionization rate. And alpha p is whole ionization rate. The ionization rates are the number of electron hole pair generated per unit length by an electron or by a hole. The equation number 2 may be written as d ion of x by dx is equal to ion of x into alpha n plus ip of x into alpha p. This is equation number 3. The total current I is given by I is equal to ion of x plus ip of x. That is total current due to electrons and current due to holes, which combining which gives the total current, and which is constant. So solving for IP of x, as this is equation number 4. So solving for IP of x and substituting it in equation number 3, we get, as from this we have IP of x is equal to I minus In of x, and by substituting this value of IP of x in equation number 3, we get dIn of x by dx is equal to In of x into alpha n plus, by putting this value of IP of x in this equation, so we get I minus In of x into alpha p, and which is equal to In of x into alpha n plus alpha p into I minus alpha p into In of x. So we get dIn of x by dx, which is equal to, or by taking this part of alpha n and alpha p towards the left side, we get alpha p minus alpha n into bracket In of x. So by taking In of x common from these two entities and taking it to the left side, we get dIn of x by dx plus alpha p minus alpha n In of x, which is equal to alpha p into I. So this is next equation number 5. If we make assumption that the electrons and holes ionization rates are equal, then we may write alpha n equal to alpha p equal to alpha. This is equation number 6. Then the equation number 5 may be simplified and integrated through the space charge region, and we get the equation number 5 as In of W minus In of 0 equal to I integration from 0 to W alpha dx. This is next equation number 7. Using equation number 1, the equation number 7 may be written as, we have the equation number 1 as In of 0, I will write here, In of W is equal to Mn In naught. Mn In naught. This was our equation number 1. So by using equation number 1 in this equation number 7, we get Mn iron naught minus iron of 0 upon I, which is equal to integration from 0 to w alpha dx. This is equation number 8. Here I have put this value of iron of w from this equation number 1, and since this Mn iron naught is nearly equal to I and iron of 0 which is equal to iron naught, then this equation number 8 becomes 1 minus 1 upon Mn, which is equal to integration from 0 to w alpha dx. This is equation number 9. The avalanche breakdown voltage is defined to be the voltage at which Mn approaches to infinity. The avalanche breakdown condition is then given by integration from 0 to w alpha dx is equal to 1. That is, when this Mn approaches to infinity, we get this condition, and this is equation number 10. The ionization rates are strong functions of electric field, and since the electric field is not constant through the space charge region, equation 10 is not easy to evaluate. If we consider a one-sided P plus N junction, the maximum electric field Emax is given by Emax equal to E into Nd into Xn upon epsilon s. This is equation number 11. The depletion layer width is given by approximately, that is Xn is equal to Xn is approximately equal to twice epsilon s into Vr upon E into 1 upon Nd whole bracket raised to 1/2. This is equation number 12, where Vr is the magnitude of reverse bias voltage. If we now define Vr to be the breakdown voltage Vb and the maximum electric field Emax will be defined as the critical field E critical at the breakdown, that is Vr equal to Vb and Emax equal to E critical field at the breakdown, and combining this equation number 11 and equation number 12, we may write Vb is equal to epsilon s into E critical square upon twice E into NB. This is equation number 13, where NB is the semiconductor doping in the low doped region of one-sided junction. The critical field is plotted in this figure number 3. Critical field versus NB for the one-sided abrupt junction, and this dashed line is for the gallium arsenide PN junction, and this continuous line is for the silicon PN junction. And here this region is for denotes the avalanche process, and this region denotes the tunneling process. We have been considering a uniformly doped planar junction. The breakdown voltage will decrease for linearly graded junction, and figure 4 shows the plot of breakdown voltage for one-sided junction, in which on x-axis the impurity gradient is plotted, and on y-axis the breakdown voltage is plotted. So this continuous line which shows for the silicon PN junction, and this dashed line shows for gallium arsenide PN junction. So this region is for the linear graded junction, and this region is for one-sided abrupt junction. If we take into account the curvature of diffuse junction as well, the breakdown voltage will be further degraded. And with this, I will stop here, and thank you.